Today we solve the in-text question from the NCERT text unit 3. The question is, the cell in which the following reaction occurs, and the reaction is 2Fe3 plus 2I minus, it gives 2Fe2 plus I2. For this reaction, we have to calculate standard Gibbs energy and the equilibrium constant. The given values are of the standard cell potential, which is 0.236 volt, and the temperature given is 298 Kelvin. The relation between standard Gibbs energy and the standard cell potential is given by this formula, that is delta G naught is equal to minus N, where N is the number of electrons, into F into standard cell potential, and F is, we all know, Faraday's constant. The value of Faraday's constant, we take it as 96500 coulombs per mole. To find the number of electrons, we have to see the reaction, and from that we need to find which is going to be the reduction half and which is going to be the oxidation half. So we see that Fe3 plus becomes Fe2 plus by gaining 2 electrons. So there is gain of electrons, so this represents the reduction half. Similarly, 2I minus, that is iodide ions, they lose electrons to form I2. And here there is loss of electrons, so it is going to be the oxidation half. And hence, since the number of electrons lost and gained are 2, so we get N is equal to 2. Let's substitute the value of N, the value of F, and the given value of standard cell potential, that is E naught cell, in this given equation, and we solve it. So this is very simple multiplication, 2 into 96500, and then the bigger numbers are there. In this case, it's always better to multiply the numbers as numerals, leaving the zeros and the decimals. So I have just simply multiplied 236 with 193 and we get this answer. Now after we get the answer, we add the 3 zeros which was there in this one. It is placed here, and then we see that after the decimal there are 3 numbers. So we count from here 1, 2, 3, and after 3 digits we are placing the decimal, and we get our answer as 45548 joules per mole. But it's better to represent the value of delta G naught in kilojoules. So when we convert it into kilojoules, we shift 3 more decimals and it becomes minus 45.55 kilojoules per mole. Next, we need to find the equilibrium constant, that is Kc, and the relationship between Gibbs free energy and the equilibrium constant is given by the equation delta G naught is equal to minus 2.303 RT, where R is the ideal gas constant, T is the temperature, into log of Kc, and we know that Kc is equilibrium constant. The value of ideal gas constant in this reaction, we have to take it as 8.314 joules per Kelvin per mole, and if we try to convert it into kilojoules, it becomes 8.314 into 10 raised to minus 3 kilojoules per Kelvin per mole. The value of R, it's better that we remember it. Now we substitute the value of standard Gibbs free energy. The value of R, 8.314 into 10 raised to minus 3. The temperature given in the question is 298 Kelvin, and we have to find log of Kc, that is equilibrium constant. So we remove the negative sign because the value which we had obtained for standard Gibbs free energy was minus 45.55. So the negative signs we cancel out from both the sides, and what remains is we take log of Kc to one side and the rest of the numerals to the other side. So we get it like this. Now to multiply such big numbers, it's better to use the log table. We take the log for both the sides, so we write log of log Kc equal to log of 45.55, and since here it is division, so we write minus, and rest of the logs numbers we write in terms of log, that is log of 2.303, and since there is multiplication between these numbers, we put the sign plus and we write log of 8.314 plus log of 10 raised to minus 3 plus log of 298. While using log, it's better that we convert all the numbers into simple logs. That means 45.55 we will write it as 4.55, and since there is a shift of one decimal, we write it as 10 raised to 1. Similarly, if we see here, it is log of 298, so we are writing it as log of 2.98, and since we have shifted 2 decimals, we are writing it as into 10 raised to 2. Log of 10 raised to 1, we know that the answer is 1. Similarly, log of 10 raised to 2, we have to simply write the answer as 2. So whatever is the power, that we write as the answer when we have to find the log of any number to the power of 10. Now we have to find the log of 4.555, that is 45 under 5. The value is 6580, and then we see under the mean difference 5, the value is 5. So 6580 plus 5, and we write here as 0.6545. The characteristic is 0 because there is only one digit before the decimal, and 1 minus 1, that is n minus 1, we get it as 0. Similarly, we find the log for all the remaining numbers, and then first we add all the numbers which are having negative sign. We get the answer as minus 3.7563, and then whatever we get after adding those numbers with positive signs, we get 4.6585, and then we add these two numbers and we get our answer as 0.9022. So log of Kc is equal to 0.9022. Now we need to find the antilog of this number, which we get as 7.984. While finding antilog, we know that we have to write the characteristic in the answer as into 10 raised to whatever is the characteristic, and then find the antilog for the numbers which are there in the mantissa, that is 0.9022. In the antilog table, we see 0.90 under 2, which is 7980. The mean difference under 2 is 4. We add the 2, we get the number as 7984, and then we put one decimal after the first number. 10 raised to 0, the value is 1, as we all know. We got log of Kc is equal to 7.984. Again we find the antilog to get the value of Kc. Value of Kc is equal to, we get 9.616 into 10 raised to 7. 10 raised to 7 because the character here is 7. In the antilog table, we find the value for 0.98 under 4, which we get as 9616. and after the first number we put the decimal sign in the answer.